theories, models, and explanations. So first up then, what is the point of a scientific theory? Well, a theory is aimed at explaining something. It is an explanans. So it is our approach at trying to understand through explanation different phenomena. And so if it is an explanation, it must be an explanation of something. That is to say, it must have some target to explain, an explanandum. But there's a lot of kind of discussion and debate as to what that target actually should be. Should it be effects or something else? Well, one of the things that I like is the suggestion by Cummings, and you'll note what I'm going to do throughout the talk is touch on or lean on literature from psychology, cognitive psychology, computational psychology, and also pharmaceutical development, and try and borrow some learnings from those that I think might be useful for us. But all of the things I'm going to present, although they're presented from the context of psychology, they are easily, with just a little bit of thought, portable over to the types of research and science that we do. So, Cummings says the primary explananda of psychology are not effects, but capacity. So things like the capacity to see depth, to learn, to speak a language, to plan, to predict the future, to emphasize, to fathom the mental state of others, to deceive oneself, to be self-aware, etc., so on. It's understanding these sorts of capacities that motivate psychological inquiry in the first place. And you can simply refer to that as being understanding the sorts of capacities of the things that we see as motivating scientific inquiry more broadly. So our explanandum is a capacity, and we can think of all sorts of different kinds of capacities of different things at different levels. So for example, we could think about the capacity for neurons to fire. We could think of the capacity for the human mind or brain to engage in reasoning. We could think of the capacity of the human body to locomote. We could also think of the capacity of groups of individuals to network and relate and cooperate with one another. Now, I'm going to focus on interventions in this talk specifically, but I think the learnings can be more broadly applied across the discipline. Much like psychology, though, as a field, we have an obsession with effects, and maybe we don't kind of talk about them as specifically as psychology does, but I think we are kind of obsessed with these. And we often talk about intervention effects. So we might be interested in, for example, the effects of some kind of exercise intervention on some kind of outcome. So exposure to the intervention produces some change in some outcome, and that's an effect, and that's what we're interested in. But it isn't really the effect that needs explaining. It's the capacity that gives rise to the effects we observe that needs to be explained. So, for example, for our discipline more generally, and thinking in the context of interventions, the capacity to respond and adapt to interventions is the thing we want to explain, not the data that we observe that demonstrate effects as a result of these capacities. So I'm going to use a toy example throughout this, and that example is STORK juice. So it's this wonderful new supplement that is, shown to be really effective and wonderful. And I give credit to Amy for this idea of STORK juice, because she mentioned it once in I can't even remember what context now, but it stuck with me, and I thought, right, I'm stealing that example to use for this. So we've got STORK juice, and STORK juice has been shown to have really good effects on performance, and you can define performance however you want, but we're going to talk in generalities here to highlight the example. So, STORK juice has been compared to placebo, and there's been improvements in performance shown as a result of this. So we might be interested in how the effect works. Well, like I said, it's not the effect per se we're interested in explaining. It is the capacity that results in the effect. So we might call it the STORK juice effect, the intervention effect of STORK juice. That is to say, when exposed to STORK juice, performance tends to improve. And indeed, this could be a really well replicated effect. It could be a large effect, and we could be really confident of this effect. But saying that one could explain the observation that performance improves with exposure to STORK juice by invoking the STORK juice effect is tautological. That's just what it is. That is the STORK juice effect. What we want to know is, how does the capacity work? So, what is a capacity then? Well, many of the things that are called effects in psychology, and again, replace that with sport and exercise science if you want, are in fact incidental to the exercise of some capacity of interest. A capacity is more or less a reliable ability or disposition or tendency to transform some initial state or input into a resulting output. So we can think of capacities in this sense. So we have the name of our model capacity, whatever we want to call it. We could call it adaptability as a result of interventions. And we have some specification of the input and some specification of the output as a function of the input. So an example, and you'll notice I lean quite heavily on fantastic work from Iris Andrui and other colleagues of hers, some fantastic work looking at how to formalize theories, what theories are about in cognitive psychology, and I'll lean on that quite heavily. Anyway, so an example they give in their paper is something like the capacity to sort. The capacity to sort a number. So the input in this capacity would be a list of unordered numbers, L. And the output would be an ordered list, L prime, that consists of the elements in L. So we have this function sorting an unordered list of numbers into an ordered list. This is the capacity that we're interested in. And it could actually be explained by a number of different things. There could be a number of different ways in which that capacity results in the effect we observe, which is the transformation of a unordered list of numbers into an ordered list of numbers. Let's say we keep doing a study where we give a particular ordered list and it always comes out with an ordering of that unordered list to an ordered list. The effect could be the result of different ways in which the capacity works. So to give the example of STORK juice, the increase in performance from exposure to STORK juice is the capacity that we're interested in, that adaptability. The input is the exposure to STORK juice, and the output is increased performance as a function of that. But that could be implemented in a number of ways. So if we know that a particular dose of STORK juice produces a particular magnitude of effect, then it could actually be that different kinds of implementations of that capacity, that is to say different dose-response adaptabilities, will result in the same effect. So for example, a linear model could result in the same magnitude of effect at a particular dose as a step model could, some sort of like threshold-based model. Now, what this leads me on to is to talk about the idea of levels of explanation. And David Marr's influential tri-level framework is something that's been applied, obviously, originally to things like cognitive psychology and neuroscience. But from the list of citations at the bottom of the screen there, if you go and look over those, it's been applied to a range of different areas, including biological fields. So I think it really is something that's applicable in guiding how we think about our theories in our field as well. So he starts off by saying there is the computational level, and that is to say, what does the capacity actually do? And that's this specification of the function of an input that is transformed to an output. We then have the algorithmic level. So how does the capacity actually do what it does? That is to say, how is it implemented algorithmically or in some sort of mathematical model? How does it actually get implemented? What does the function's nuts and bolts and mechanics actually look like? And the last level is the physical level, and that is how is the capacity actually physically realised? That is to say, what are the underlying structures that implement that capacity? What are the underlying structures that result in that kind of mathematical model that we see at the algorithmic level and explain the capacity, that is to say, the function of some input that produces some output? To continue the example that they give in their paper, Van Vory and Baggio give in their paper, the sorting capacity, as I said, could be implemented by varying different algorithms, and those algorithms could be implemented at a physical level by varying different things. So a computer could implement these algorithms, so could a human brain, so could a monkey, so could Hungarian dancers. The Hungarian dancers thing makes sense if you actually go and read their paper. There's a link to a YouTube video where Hungarian dancers are dancing through the selection sort, for example. In fact, there's a strange number of these Hungarian dancers and sorting algorithm videos. So feel free to go have a look at them if you want. But we could think about this similarly for STORK juice's effect, or the capacity to adapt to STORK juice. So at the computational level, the function is essentially that performance is increased as a result of some function of STORK juice as an input. And at an algorithmic level, there could be different ways in which that is mathematically realised. And at the physical level, we could, for example, take those mathematical models and we could implement them as a computer simulation. So they could be physically implemented, that capacity of, we could label something in the algorithm as STORK juice and something as performance, and specify the mathematical model by which performance changes as a function of the input STORK juice. But of course, we're saying that there is some evidence that this occurs in humans. The capacity is present in humans and can be realised and implemented by humans. And maybe there's some animal studies as well that's shown it occurs in rats as well. Now, what I want to focus on is not necessarily that physical level, but I want to focus on this idea that, of course, the capacity is what we want to explain, and that capacity is essentially some function or some output as a function of some input. But it's the algorithmic level here, I think, that really helps to guide what we want to do when it comes to the types of research that we actually, empirical research that we actually engage in. So let's continue with the STORK juice example. So let's say that, for example, we've got a pretty good body of literature showing that the effects are fairly large. Let's say it's something like 0.9 standard of a standardized mean difference. So the improvement in performance is 0.9 standard deviations. So that's a pretty good effect. Let's say as well, most of the studies in the field have about 10 to 15 people per group, and given the effect size that we've seen, they've got reasonable power to detect it, even in a parallel group design, but also within participant repeated measures design as well. Let's even say that actually, we've got enough evidence with these small samples that we've got a pretty good meta-analysis that supports the existence of this STORK juice effect. But let's say, for whatever reason, and just follow me with the example here, let's assume that for some reason only a particular intervention dose has been examined. And, this could be because of tradition, whoever came up with STORK juice said it should be implemented in a particular dose, and everyone's just continued to follow that as a community norm around it. There could be logistic things around it. There could be some issue, it's expensive, or maybe, there are limitations to how it can be dosed, or something like that. Whatever you want, it doesn't matter. But for what our purposes, let's imagine that we've just had a bunch of studies that have looked at a particular dose compared to, say, placebo, and we're confident that that produces a pretty large effect. But people do start to wonder about the possible comparative effects of different doses. We see that adaptation to STORK juice occurs and wonder what the shape of that adaptation looks like as a function of STORK juice and the different levels of STORK juice, different doses we could produce. Now, some people start doing some comparative trials, but the results are pretty inconsistent. I mean, they're still using the sorts of same sample sizes as previous studies have used. But despite this, some experts have started to postulate, and there's been a few opinion pieces and some narrative review articles, and maybe even some attempts at sort of trying to synthesize meta-analytically some of the data, and people are starting to come up with some ideas for some speculative dose-response models. So, for example, they might say STORK juice has increasing effects based on how much a person is exposed to. Up to a point, STORK juice increases performance, but then it reaches a ceiling effect. So maybe this person thinks there's some sort of rate-limiting step involved in the adaptations that are produced. And, maybe there's someone who says there's an optimal dose, but it's actually less than what is typically used. And after that, then performance actually starts to decrease. So, whatever, maybe people have got a bunch of these verbal theories about what the dose-response model of adaptation to STORK juice looks like. So these are verbal theories. These are intuitive ideas about what, how, and why a phenomena about the what, how, and why of a phenomena based on empirical observations and domain knowledge. So say we've got these loose inconsistent observations of possible comparative effects. That's contained within the body of domain knowledge that there is definitely an effect of at least this dose. And maybe there's some also a little bit of mechanistic work that's been done that maybe hints at sort of different dose response models from a mechanistic sense. Verbal theories, then, they express the structure of the theory in words, and as a result, they're limited by the imprecision of natural language. So this is an issue because this is what we typically have in our field. We have very few kind of very specific formalizations of the theories we have. We have typically verbalizations. We have typically theories and models written in natural language, which produce imprecision. They are imprecise. They make it difficult to draw deductions from. And this is an issue because, as we say, typically a verbal theory's ability to explain a phenomenon is just simply asserted, and that's problematic because to demonstrate that the theory explains the phenomenon, we must first show that the phenomenon does indeed follow as a matter of course from the theory. So in other words, explanation presumes accurate deduction from the theory. And the problem with verbal theories that are not formalized is that they're deductively infertile. They're substantially constrained in their ability to provide clear explanations because we're not exactly clear what is entailed by the theory itself. Good theories produce very, very specific deductions. They specify very, very specifically what effects we should see as a result of that capacity that we're trying to explain. They tell us what observations we should make, and those are the effects in essence. They have what is called a clear Spielraum. Now, this is a phrase that was used by Paul Meehl, or coined by Paul, not coined by Paul Meehl, but incorporated into Paul Meehl's work. I believe that various people within the Vienna Circle used the term earlier. Anyway, it's a German word, and it basically means range, or scope, or elbow room. Whatever. But what it does is it denotes the range of logically deduced possibilities given a theory. So, if we were to assume that the theory were indeed a true explanation of the capacity of interest, then what effects would we expect to observe? What could we deduce from the assumptions that are built into the theory? And this is a major component in assessing a theory's problem-solving power. That is, its ability to predict numerical values and function forms of observational data. So we can then go out and conduct studies that act as severe tests of those theories' predictions. So what kinds of Spielraum could we have? Well, we could have a theory that merely deduces a directional hypothesis, so that there is an effect and it's positive or negative, or whichever way you want to go. We could have a theory that is a little bit stronger, but it's still fairly weak. It predicts that the effect should be within some range, but it's quite broad. Stronger theories would make narrower predictions until, if we were really good, we might be able to make point predictions from our theories as to what we should go out and expect to observe. They can also predict functional forms of data. So in the example we're going through here in terms of intervention effects, it might predict the shape of the dose response model. So it could be linear, it could be some sort of plateau, it could be some sort of quadratic function. The thing is, all of these things are very important because they help us to actually plan studies better to then test our explanations for the capacities that we're interested in. And it's this formalization that leads us to be able to actually improve the research that we do, or at least I think. So we're going to move on to the second section then, which is to say we're going to talk about how this formalization can help us use things like simulation to plan studies. And I'm going to lend from, or borrow from, the pharmaceutical world here, because in that world, trial simulation is key. It's used extensively. Now, let's ignore the fact for the moment that they have obviously a hell of a lot more money than we do to actually do these kinds of things. That's not what's being debated here. But in principle, most of what they do, we could at least try to do. It might just be a bit harder. Anyway, trial simulation in its simplest form, is essentially a clinical trial simulation is the study of the effects of a drug in virtual patient populations using mathematical models that incorporate information on physiological systems. Now, system is actually an interesting word because that's the word that Marr originally used, not capacities. But essentially what we can think of here is that in trial simulation, we have some system or capacity, that is to say like adaptability or response to a drug that we want to explain with a mathematical model. We could also, for example, talk about how that is actually implemented physiologically. So, for example, what are the kind of underlying molecular and cellular mechanisms that, are the mechanism of action through which a drug works. Anyway, the phases of drug development, many of you may be aware of this, but of course, most of this is preceded by considerable preclinical pharmacokinetic research. So they have a much stronger base of perhaps what to expect, given their understanding of how exactly drugs, these drugs are proposed to work, what their mechanisms of action are supposed to be. But in essence, there are 4 stages. We have the first in-human studies, which are dose-ranging studies, where they actually test varying different doses. Then we have small trials looking at efficacy and side effects. Then we have larger trials looking at effectiveness and safety. And then we also have post-marketing surveillance of effects once a drug actually goes to market. The thing is, throughout this entire process, there is the implementation of formal theory and models at each step, and simulations from these to see what they deductively entail to aid in the design of studies. So, for example, in phase 1, those first in-human studies, the dose-ranging studies, the doses that are selected, will be informed by simulation from information at the preclinical pharmacokinetic stage about what the mechanism of action is and how we think that might be mathematically described. Because, you can't just throw every, as much as money as they have, they've not got infinite money. So you need to be able to design studies efficiently and well. I mean, that's maybe why they have so much money, because they can do this. When we move through each phase, information from the previous phase, both in terms of the implementation from a physiological level, but that mathematical model is used to improve and simulate and iterate and test, and then used to simulate the next steps in the study or in the phases of development, the next studies that will be coming. So let's think, of course, we're not able to necessarily do this as well as them, but let's just think a little bit about how we could maybe take some of our verbal theories and make them a bit more formal, at least think about what they mean. So, for example, let's take the idea that stork juice has increasing effects based on how much a person is exposed to. That seems to entail some sort of linear model of dose response. So increasing stork juice has an increase, results in an increase in performance. Now, let's say, for example, we've had these studies that have found this sort of effect. If we've got placebo on the left-hand side of the x-axis and on the right-hand side is the usual dose, that the magnitude of change, that is to say the slope between placebo and that dose of stork juice, is roughly that effect. This model might deductively entail that if we doubled the dose, we would see double the performance effect. So we can think about, how plausible that is and whether it's a model that we want to use to potentially design studies and test, whether it's, sounds like a plausible explanation and worth exploring. We could look at this one, up to a point stork juice increases performance but then reaches a ceiling effect. So that sounds a bit like a linear plateau model. So there's some sort of linear improvement up to a plateau. Like I said, maybe there's some proposed rate limiting effect. But if that's the case, we might expect to see a model that looks something like this. And so we could, think about what studies need to be designed to test that and see whether we observe those effects. And lastly, there's an optimal dose that's less than the typical dose used, but and after that, performance increases. So this sounds a little bit like some sort of quadratic dose response model. Formalising our theory, and formalising our proposed dose response models supports the ability to then simulate from them. And we can simulate from them to then help plan the studies that we want to look at. So these are, in drug trials or in drug development, they simulate a host of candidate models to potentially explore. And they'll think about, what seems most plausible and also what they've got resources to look at. These are, for example, a bunch of different possible dose response models, and they've been parameterized as well. You can see the individual simulated participants. They've been parameterized such that on the very right hand side of the x-axis is the typical STORK dose, on the left hand side is the placebo, and they've been parameterized to show that 0.9 standardized mean difference. And we could look at a bunch of different doses relative to that typical dose. We could look at the red line, 50% of the normal dose, or the green line, 70%, or the blue line, 90% of the typical dose that's implemented. And from these models, we could simulate drawing participants from them, from that proposed mathematical explanation of the capacity of interest, the data generating process. We could then simulate actually selecting people at random and running trials. And we could look at how much power these trials might have to examine different comparative treatment effects. And so, like, for example, here, you can see in some cases we've got pretty good power to draw comparisons between what the models might propose would be the difference between, say, 50% of the normal dose and the typical dose. But maybe for other things, like smaller differences in intervention, 90% versus the typical dose, maybe we've not really got that much statistical power. And for those of you who prefer estimation and precision of estimation of parameters, we could simulate it to also look at confidence interval width for the effects that are being estimated across a range of sample sizes. Anyway, I'm quickly running out of time, so let's move on then to what this all really means. What are the broader implications of engaging in a much more formal process of thinking about explaining the phenomena, that is to say, capacities within our field that we're interested in? Now, maybe going through this, you thought the toy example I was using seemed a little bit too real. And there's a reason for that, because it kind of is. I used real data and real ideas and just labelled it as STORK juice. In fact, the general effect size 0.9 standardised mean difference actually reflects a typical intervention effect that I work with, which is the effect of resistance training to momentary failure on strength when compared to control. So that's to say resistance training compared to doing nothing. And I'd wager, to be honest, it's probably one of the biggest and most reliable intervention effects the field has. We pretty much know that if you do this, then you're going to get stronger. But even considering that, one of the things that people are interested in is the dose-response relationship between the intensity of effort of training and the adaptations that are produced. And considering this, most of the studies seem woeful in their ability to actually examine many of those dose-response model candidates, particularly as we get closer and closer to that maximum dose that we can implement, that's to say, people training to failure. And this is only really evident when we start to formalize carefully what we actually mean in terms of these dose-response models, to then think about simulating to design studies to test the ideas. So, I mean, this is worrying in a sense. So a question could be, what can we do? And I'm going to run through really quickly just some ideas here and leave them with you to think about. So, for example, I've said about moving towards being a theoretical science. Maybe we could just stick to being applied, and we could say, look, we're just interested in particular operationalizations of outcomes, and what we care about is whether intervention X produces a change in this operationalization. We don't want to necessarily explain the capacity. And as such, we might just think instead of looking at the smallest effect sizes of interest that are meaningful in some other sense, rather than predicted by theory. We could spend a lot more time on concept formation, measurement development, theory development, and so on to actually build these better theories. Rather than trying to move straight towards it, we can spend more time working on the formalization. We could start to, as I've said before, leverage some of these large observational data sets. Maybe we can link better to sports teams, industry, and tech, where a lot of data is being captured, and use these to potentially test some of our ideas. It's something that we've been doing recently, working with some very large data sets. We could follow in the lead of pharmaceutical industry, who typically have run for a long time large multi-center or multi-site randomized controlled trials, or psychology, who have implemented the Psychological Science Accelerator, where different groups of collaborators can come together to conduct a much bigger, more rigorous study. Or we could just continue with the current approach of small studies, but add the caveat that we become more epistemically modest in the wait for sufficient evidence to accumulate to then allow us to perform robust synthesis to test some of these ideas. Maybe individual studies are just reported descriptively. We don't draw broader inferences from them. Or if we do, we're very modest about the fact that these are inductive inferences drawn purely from these observations. They're not deductive tests or the tests of the deductive propositions entailed by our theories. Now, you might be thinking, is this even worth it? Christ, this all seems like a lot of hard work. And as much as we probably hate to admit it, most of the effects in our field are likely very small. I mean, it means that this is going to be very hard to work as a theoretical science to try and understand the capacities that we're interested in. Testing these ideas is actually going to be very, very hard. But we could say, are the effects small enough to care about? But some people in our field do say that they matter. They do say that they care about small effects. And so the last thing I think I'll say is that those who do claim that small effects are important, really the burden's on them to actually do this process of formalization, to then design the right kind of studies to actually test the capacities that they think lead to these small effects that they think actually matter. Anyway, I'm going to leave you with this final clip, which is a slide or a panel from one of Nathan Pyle's Great Strange Planet comic strips that says, "Sometimes science is so difficult it makes me sad," which I've actually got as a t-shirt as well. I should have been wearing it now. Anyway, 3 quick conclusions then from the 3 sections that we've gone through. So, first off, engaging with theory and model formalization, I think, can help us understand what theories really imply about the capacities we want to explain. 2, I think knowing this aids us in better planning the studies that we want to do in order to detect the effects of those capacities and therefore test our explanations of them. But 3, this formalization, I think, shows us just how difficult our science can really be, and as a field we need to decide what route we want to take forwards. Thank you very much. I appreciate I'm a few minutes over time. Hopefully that's only into the potential time that we have for questions, and I've not into Paul's time, so I will leave it there. Thank you so much. I hope you really all enjoy the rest of the conference.
Awesome. Really nice talk there. I have to admit that's one of my learning goals for the year moving forward, is get better at modelling and thinking at a kind of higher level about what it is I'm really trying to do. So I was super excited when I saw that talk by James coming up. I'm going to stop the recording on that one.